Okay, we good? Can you hear me in the back now? Oh, way in the back. Okay, cool. First of all, thanks everybody for coming out, and thanks to our hosts and our wonderful organizers for getting everything set up. I'm going to talk a little bit today about machine learning on a single node. And what I mean by that is, you don't have a cluster, you don't have a Spark cluster, if any of you have heard of that, you don't have a Hadoop cluster, nothing like that. Just what can you do with one computer? And just so I have an understanding of kind of the background of everybody in the audience, we saw one data engineer earlier, Christian, I don't know where you went. Anybody else here doing machine learning, data science type stuff in your day-to-day job? A couple? All right. Software developers? Who's doing software development? Okay, perfect. So one important thing to keep in mind about this topic is you don't need to be like a data science or machine learning person to do machine learning. It's actually not that difficult, and if you're a software developer, then you pretty much got all the skills you need. So if you like the stuff that I'm talking about, you think it's great, find me on Twitter, #Drake, #hacker. If you think the stuff that I'm talking about is completely crazy, and you don't like it, #Drake, #thought leader. And between us, we will know who's voting who's right. Background on me. I studied applied mathematics. That was my sort of formal education. But I went back to school, actually. I worked in tech for years before I actually went back to university. But I did study math when I went back. And now I do advising work for growth stage startups. And what that means is I see a lot of different growth stage companies. They typically have product market fit, they're growing very rapidly, they have users, and the problem is they just can't quite scale some things. And sometimes that means they don't know how to scale people and process type stuff, and sometimes that means they don't know how to scale technical stuff, especially machine learning related stuff. So I typically work with them and help them on those topics. So my claims for the talk are that, first of all, RAM is growing faster than data anyway. So everyone's probably heard all the big data stuff now for the last 5 years or so, and data volumes are growing, but RAM is actually growing faster. So your access to what you can do in terms of processing data on a single machine is growing faster than the data that you're collecting in general. There are many techniques for dealing with so-called big data, and some of them actually don't require very much in the way of system resources. And lastly, one machine is fine for machine learning. So just as an example in the audience, is anyone doing any sort of data analysis, whether you're a data person or a software developer? Okay, some folks. Anyone doing data analytics with data sets more than 5 terabytes? One. Tap the nice guy. Okay, one. But that's actually, that's a good example of what I'm going to go into. This is a slide from Cray Computing. Anyone remember Cray? Yeah, but me and 5 other people. Okay, Cray is a supercomputer company. They were one of the first supercomputer companies. And in this slide, what they're talking about is they're saying there are these big compute clusters for all these different stages. So you have a kind of compute big cluster thing, whatever infrastructure, for extraction, transformation, loading of data. You have another one for your sort of analytics and data mining, and then maybe you have some other ones at other steps along the way. And they're all siloed. So in some sense, they're detached from each other. And this becomes a real problem in organizations that are growing very quickly, because you end up with systems that have different sets of data that don't really talk to each other very well. And the people who work on those systems also don't talk to each other, and that creates quite a few problems. So if you can minimize the amount of infrastructure you have, you also minimize the cost, which is great, but you have less maintenance, and it's easier for everyone to reason about the systems that they're working on. So let's say you have a big data set. Has anyone run into a problem where you're trying to do analytics or machine learning on a data set, but it's too big, too big. You don't have enough RAM for it. Okay, great. So step 0 in solving that problem is add more RAM. And I know that's like not the super cool horizontal scalability story that everybody wants to hear, but RAM is pretty cheap. And if you look at the rate of increase in how quickly the size of data set people are analyzing are going up, this graph's actually moving to the right year by year. So you can look at it. I don't think it's okay, perfect. So this is a cumulative distribution. And so when you get to about 80% of people, they're dealing with data sets that are right around 100 gigabytes plus, which is not outside the realm of possibility for normal stuff. But you'll see that as the years go by, the data sets get a little bit bigger. And if you put that on a log plot, what you'll find is that the data set size increases about 20% per year. So if you're doing analysis on 100 gigabytes this year, you're going to do analysis on 120 gigabytes. 20% year-on-year increase. Now, contrast that with the RAM increase rate. This is for Amazon for EC2 instances, but it's a general concept. The size of the available RAM is going up by more like 50% or 100% per year. So if your data set size increasing by 20%, your RAM is going up by 100%, you don't really need a big cluster. You can just buy a machine with more RAM sometimes. And just, now that a lot of it might be important to do it. The current large motherboards from Thailand can support 12.3 terabytes of RAM. Does anyone have 12.3 terabytes of machine learning data? Like actual data for machine learning, not just data, but data they're using for the model. Datasets guy? So? Okay. So you can get a big server, it'll get cheap. Well, not cheap. Okay. If you can't add more RAM for some reason, what you can do is you can sample the data. So you have a really big data set, maybe you don't need to analyze all the data. And this was the problem people started running into about 2008, 9, 10-ish, where we had this big data hype thing, and people wanted to do machine learning on these large data sets. And they completely forgot like 300 years of mathematics. And instead of just sampling and doing some reasonable statistics on this data, they said, well, we're just gonna analyze all of it. Our sample size is our data set, and then magic will happen. Well, you can still sample your data set. It still works really well. And one example is an online advertising. I don't know if any of you work with online advertising, but typically you have something called a click-through rate. So how many people have to see an ad before somebody clicks? And the answer is a lot. It ends up being about 20 clicks for every 10,000 views. That's kind of a so-so click-through rate in the advertising. And what that means is you can pretty much just drop 90% of your data before you start training your machine learning model, and you'll be fine. It won't be any big deal. And this is a point of contention people often have when I talk about this topic. So any point of contention here about why I can't drop a large portion of my data in a biased sample? No? Wow, nice audience. One. Ruins my p-value. I'm not worried about my p-value. Sorry? Oh, that's okay. I don't need the label. That's fine. No problem. So what if sampling doesn't work? Okay, fine. So we can't add more RAM, and for some reason we can't do sampling. So we still need to have access to our whole data set and use it for our machine learning problem. Okay, well, let's just change our perspective a little. And instead of considering this whole big data set as one thing, let's kind of pretend it's a stream of data. And we're just looking at one record or a batch of records at one time. So we'll reformulate this problem a little bit. And what we need to do is we need a data source that we can turn into a stream. We need something that allows us to do stateless feature extraction. And for the non-data folks in the room, when you're training a machine learning model, you need to supply it with features that it can use to learn. And when you extract these features from your data set, one way that you can do it is in a way that doesn't depend on any features that came before or that will come afterwards. So you only have to worry about what you're looking at in that moment. Data that's going to come later, you don't care. Data that's going to come in the future, you don't care. So you want to have stateless feature extraction. And you need a model which supports incremental learning. So you need a machine learning model that can operate on these chunks of data instead of all of it at one time. Creating the data source is not big enough. So Python people, how many people in the room do Python stuff? A couple? Okay. So you can write a generator in Python that will output your records for you. Or if you're using pandas, which is pretty common in the data science world, there is a chunk size parameter you can pass into the read CSV method that will just give you like 10,000 lines of a file at a time. So creating this stream of data is not really that big a deal. The stateless feature extraction part's a little more complicated, and I'm going to have 20 minutes for the talk, so I can't go too much into this. But essentially what we're going to do is we're going to take the feature names and the feature values, we're going to concatenate them together, then we're going to hash it, and then we're going to use that hash, whatever that number is, as the index into an array of weights. So when we're using this data to build a machine learning model, we're going to have a big array of weights, and whatever features are coming, we're going to create a kind of weighted result based on those features. Sorry, what was it?
So heuristics.
Where are you again? Oh, yes.
Heuristics.
Heuristics. Not heuristics. Not exactly. We're think about it like you have a big list of weights, and instead of storing the actual feature names and the actual feature value and doing stuff like that, you're actually just going to hash it, and you're going to use that sort of combination, that hash, to indicate where in the weight array you would make modifications. Yes, sir.
So we call that discretizing, making it discrete, right?
Making what discrete?
Yeah. So floats get turned into like integer right?
Okay, that's a slightly different question. That's what you do when you have categorical versus continual variables, right?
But the effect of what you're saying is to do that.
It would have that effect, but it's actually okay. And we can talk about why afterwards. We're a little bit time limited. But it's a good question. It's a good question. So what you do for the feature extraction is you take in all these features in your data set, and you turn them into indices into an array of weights that you can use to make predictions.
Sorry, does this help with, in the future, if you want to remove the data points from it? Would this help?
Remove the data points?
Yeah, from the calculation.
Sorry, I don't understand. Remove the data points?
Yeah, so you put a hash on these features, but in the future, if I want to remove certain data from my calculation, will this help?
I don't know that it would help. I'm not sure I understand the question, but let's talk about it. Okay, good. The other advantage to this is that when you use a hashing trick, you can configure in advance how much memory you want to use for your model. And this is really important. If you have 2 gigabytes of memory available, use 2 gigabytes long array, or 2 gigabytes array for your weights. If you have 2 megabytes, use 2 megabytes. Not a big deal. And your algorithm for the hashing part doesn't actually care one way or the other. If you notice, there right before the return, I'm actually doing mod max weights. So how many weights I have in my model, that's pre-configured. So it's a very nice feature, especially if you're doing machine learning on smaller systems. Incremental learning you can do all over the place in scikit-learn for anyone who's doing machine learning stuff with scikit-learn. There are many models that support incremental learning. Anything with a partial fit method you can do, but I'm not going to talk too much about scikit-learn. You can write your own, actually. This is the whole code for logistic regression with adaptive weights, adaptive learning weights. And it's not that long. I mean, for the software developers that are in the room, like, this is it. When the data science folks are talking about the stuff that they built for whatever prediction, like fraud detection or whatever, that's it, sometimes, most of the time. And the performance on this is not bad. So with just regular C Python, this is about 20,000 records per second on this laptop, which is not like some huge massive laptop. It's actually an X series ThinkPad, so it's the portable one. It's not the supercomputing one. So 20,000 right off the bat. Does anyone here, besides maybe the Tableau folks, have a system that has to do 20,000 predictions per second? No? Tableau 20,000? You got it? Okay. This is what you do if you're using Python and it's too slow. You just replace Python with PyPy. And for the folks who aren't familiar with the Python world, PyPy is a drop-in replacement for the Python interpreter. It's a JIT compiler, and it's much faster. In this case, without changing the code at all, you get a 3.5 times speed up just by using PyPy instead of Python. But what we really want to do is we want to use all the cores that we have available. We want to use all the cores. Python is single-threaded, so you can only use one core at a time, and that makes things not as fast as they could be. And because we're using all the cores, we want to use shared memory. So we want to lock the memory to make sure that multiple threads aren't modifying the weights all at one time, because that could cause problems. The problem is, as I mentioned, Python is single-threaded. So only one Python thread can execute byte code at any given time. And because of that, you can do stuff with multiprocessing, which gives you multiple Python processes instead of multiple Python threads. Now you're essentially running multiple Python interpreters all at once in your own process, but they have to communicate. So you can communicate via shared memory with something like a raw array, which is nice, but if you want to have a lot of workers, you do something like this. You take your data, you put it into a queue, and then you have the workers pull the data out of the queue and do whatever machine learning stuff they want to do, and update the model. So now you're using 4 cores instead of just 1. So it should be faster, but it's actually slower, which most people don't expect. So then the question is, why is it slow? So now you do call environment, you look at the call graph, you say, what kind of stuff is my system spending time doing? Well, I have a Python script, there's a put method, and then there's this thing. Right here. You probably can't see the numbers, and that's okay. The problem is it's yellow. That means it's taking a long time. And the reason it's taking a long time is because it's waiting to acquire a lock to put data into the queue. So it's spending 64% of the actual runtime to train the machine learning model just waiting to get a lock to put something into a work queue, which is not ideal. And the problem here is we're starting to get to the end of what you can really do reasonably with Python. Python is a great tool, I use it all the time for exploratory data analysis, but when you want to start doing higher performance machine learning stuff, it's not really designed for that. So there are things you could do beyond this. You could look at lock-free queues in Cyclone or build your own extension module or something for Python, but we're starting to like have a square peg in a round hole situation. So we'll rewrite this in Go, which is actually pretty much the same as Python. So if you look at the Go version, this is the exact same output. This is the Go version. This is the Python version. Pretty much the only difference is the braces. So if you don't like braces, sorry about that. But that's about it. Still a single thread, actually, in Go, unless you use multiple cores. But you get a big speed up, actually. So now you're up to 186,000 records per second, just from going from Python to Go, which is nice. But we can do better, because in Go, we can easily use all the cores on the machine. So instead of having one worker running in one core, we'll have 5 workers, and they'll run across all the cores of their own machine. Okay, now we're getting somewhere. 253,000 requests per second over 20. So we've got an order of magnitude increase. Now, if we consider stochastic gradient descent, which we're using here, if you don't understand this math, that's fine. It's not a big deal. The problem that's an issue is this area down here where we're updating the weights. And because we have multiple threads that may touch this memory all at once, we're locking this section of memory before we make modifications, just to keep it consistent, because we want it to be thread safe, right? So all the developers in the room, have you heard about thread safe stuff before? Somehow? Yes, okay. So we're being good developers, and we're doing everything very thread safe, very thread safe. But it's not that efficient, right? Because you still have to wait for locks. So how do you make that better? Well, you can do round robin for your locks. So instead of trying to acquire a lock, you can allocate locks in a round robin fashion. So that's actually technically better. There are some papers on this. It's a bit faster, but it's kind of a pain. So you have to do orchestration, it's not great. But then you can ask yourself, like, what if we just ditch the locks, actually? What if we just leave this memory open and let all these processes update stuff all the time on this machine learning model? Does that kill our accuracy? Like, does it just destroy any consistency on the weights? Like, what happens? And it turns out there's a really nice paper on this topic called Hogwild. So if you haven't read it, it's a great paper. It's out of Berkeley, I think. And it goes into a lot of detail on the analysis of how you can do stochastic gradient descent in a parallel way with no locks and what happens. And the short version is that the algorithm actually gets better. So your accuracy actually improves if you don't use locks. The reason is that your model becomes a little more generalizable. The kind of conflicts that you might prevent if you have locking actually serve to make your model a little bit more robust. It's kind of like injecting some noise into the system. It's way faster. So these are still the numbers on my laptop, by the way. I just reconfirmed these benchmarks like 2 days ago. And on my laptop, this same benchmark gets up to 360,000 requests per second. Analytics, you beating that? Why don't you run it on a laptop? You good, right? I should also note this 360,000 is without any further optimization. So if I were advising a company and I was helping them with scalability on this topic, this is using regular string concatenation, which everyone probably knows string concatenation varies in units. If I were doing this in production in a company, we'd be using raw bytes and doing everything that way in fashion. So this is not the limit of performance on my laptop. So for anyone who's thinking in the audience, oh, we have some data, it's not going to fit in RAM, we need a new cluster, we need a Spark cluster, we need some other kind of cluster, probably don't need a cluster. You might just need to rethink a little bit how you're analyzing data. And I'm happy to take questions. Do we have time for questions? Okay, questions? One, yes.
So it is with Python, one of the strengths is the vast number of libraries that are available, right?
Yes.
So if you wanted to do another algorithm, would you have to understand how it's kind of made and then replicate that in code, or would you do it with something similar?
So there's no question that Python library ecosystem, especially around data science stuff, is phenomenal. I think it's the best. I don't think it can be. What I've found in my advising experience with companies, and to be fair, most of the advising work I do is about leadership and people in process. I don't get to have that much fun with the tech stack anymore. But most of what I've seen is when you want to put these systems in production, and they have to process a lot of data very quickly, the Python libraries, usually that's more used for the prototyping stage. Once it starts to get big, you have different problems. And that's especially true if it's high frequency. So there's some people that will write stuff in Python, they'll put it out on a Spark cluster or something like that. It's a little bit different situation. So a lot of the systems I work on, they're really high performance, they have low latency requirements, they have to do 400,000 or whatever records per second. And so Python is really not a great fit for that. But no question that library ecosystem is great. But what I've also found is most of the machine learning models used in practice are not that complicated. 80% of the time or more, you're probably doing some kind of binary classification with logistic regression. So you can do that yourself. If you want to do stuff in TensorFlow or deep learning things, there are go bindings for that. So it's not really all that different than using something like Keras in Python. But the performance benefits are pretty good. Depending on how much computation you do on the Python interpreter versus how much you're doing like in the C libraries. Did that answer your question? Cool. Anybody else? Other questions? I know it's a lot of material, so if you want to talk afterwards, just find me. I'm the guy with the beard. Thanks again for your time.